Bismillahirrahmanirrahim. Assalamu alaikum everyone. I hope that you will be watching the videos, and it is important that you give some attention to these videos and also read your notes and your chapters. Anyway, so today we will be actually looking into the adsorption processes that are taking place on the electrode surface and from the solutions in which the electrodes are immersed. So first of all, we just need to remember a few things. That is, the electrode processes that actually consist of two processes, that is the Faradic electrode process and then we have the non-Faradic electrode process. So the Faradic electrode process, as you may remember, is the one in which the heterogeneous electron transfer is taking place, and the non-Faradic electrode process is the process which is other than the electron transfer process. So actually adsorption, which mostly doesn't involve heterogeneous electron transfer, is a non-Faradic electrode process, and it leads to the formation of electrical double layers that you have studied initially, and you saw that how the potential drop across these double layers take place. So anyway, we will be looking at this, and to do that we will be looking at several things, and we should keep actually several factors in mind. So for example, for adsorption to take place on electrodes, we need to remember that we have these solvents and then we have these solutes, and which are present or which are part of the solutions. They are components of the solution. So these components actually affect the adsorption process. Then in adsorption process we are looking at adsorption, which consists of adsorbents and adsorbates. So adsorbent is the one on which the adsorption is taking place, that is the surface on which the adsorption process will take place, and the adsorbate is the one which is getting adsorbed. So in our case, the surface of the electrode will be the adsorbent, and the solute, or maybe the solutes, there could be many solutes, like analyte is a solute, then we have other solute like maybe a supporting electrolyte is also a solute, and there could be other like some impurity which should be avoided. So there could be many solutes. So all of these things which are present, which I have written over here, could be the adsorbates. Now the electrode surface is important. Electrode surface is actually the exposed surface. We are looking at the exposed surface, and then when the electrode is just immersed in a solution and there is no charge due to the external power supply, so there could be some inherent surface charges on the electrode surface, and obviously when the electrode is connected to an external power source, then the situation will change, and a charge will be present on cathode and another charge will be present, and opposite charge will be present on anode. So those kind of situation will lead to different kind of interactions, and there will be different processes due to this, and then we will be interested to know that what is the possible mechanism of adsorption that is actually happening. So anyway, now if we look at the electrodes, there could be different kind of electrodes. This is a simple glassy carbon electrode. You can see that this one have a different exposed surface when compared to this one and this one, and all of these electrodes have a different exposed surface. So this part over here, which is present here, is actually the exposed surface. This one, or this part, or maybe this part is the exposed surface. Similarly, we have another kind of electrode over here. You can see that there is a mercury drop hanging at the tip of the electrode, and these are hanging mercury drops, and they also form a renewable surface. So on all these surfaces, basically the adsorption can take place. Similarly, we have these platinum electrode. Again, they are of different shapes, but essentially they are platinum electrode and they are offering different exposed surface area. So these are some common working electrodes which surface can be used to perform different type of electrochemical processes. So here is an example of the similar kind of process in which actually this nitrate ion is converted to somewhat a different moiety, which is non-toxic, because nitrate ions are toxic. So different methods are actually used to get rid of the nitrate. So this is basically an example of the nitrate removal cell in which the adsorption process is also taking place, and adsorption is used as a way to remove nitrates from the polluted water. So anyway, you can check the details. I will give you the link of the paper in the description or in your course Teams account. So you can actually study if you want to check the details of that. Anyway, so if we move forward, we see that so what we see is what is happening to nitrate. Actually, the reduction of nitrate is taking place, and we can see that this is the HOMO of nitrate and this is the cathode. And when we apply some electric potential, then the energy of this electron is raised, and this actually move to this part as is shown over here, and the LUMO of the nitrate is filled, and this way the reduction of nitrate is carried out electrochemically. So this is also from another paper in which the electroreduction process of nitrate is carried out, and it is converted to NO2, and which can also be dimerized to actually N2O4, and then further converted to other products which will be less toxic. So anyway, again, for removal, it is about the removal of nitrate ion. So you can see that these processes have some practical applications and can be really very useful, in which the adsorption and other electrochemical processes are involved. So now we will look at adsorption in terms of equilibrium. Here is this process. We see that here is this solute ion which is solvated by solvent molecules, and it is coming near to the surface of electrode, which is over here. And when it comes near to the surface of electrode, there are several solvent molecules are present which are pre-adsorbed on the electrode surface. So when it comes near it, it can actually replace, that is, after losing a solvent molecule, it can replace a solvent molecule near the surface of electrode and can adsorb directly on the surface of the electrode over here by replacing the solvent molecule. Now this adsorption which is taking place is depending on many factors, and one of an important factor is the hydrophobicity of the adsorbate. So it means that increasing hydrophobicity or decreasing hydrophobicity will actually affect the process of adsorption which is taking place during this equilibrium. Now, the electrostatic attraction between an ionic adsorbate and a charged electrode can matter a lot. And obviously, once the electrode is connected to the power supply, the charge will vary significantly and the electrostatic interaction or attraction will also be changed. So the third one is the adsorbate electrode bonding, which can also be a factor and can affect this adsorption in terms of equilibrium. So in other words, here again, although there is no electron transfer, but still the nature of charge on the adsorbate ions and on the adsorbent will matter, and this can somehow be affected by the external power supply which is connected. Now, the process of adsorbing species have some classifications, 5 classification by scientist Anderson, and the first one is that the simple inorganic anions and cations are given the name class 1A, and these inorganic anions and cations are basically weakly solvated such that electrostatic attraction between ionic charge and an oppositely charged electrode surface can pull the previously discussed reaction to the right. That is when it is weakly solvated. So this is basically a solvated ion, and if it has a tendency to lose these solvent molecule, if they are weakly solvated, so if it easily move these molecules, then it means that it can go and easily adsorb on the surface of the electrode. Now, these type of ions involve this ClO4 negative, and then, or in other words, perchlorate, or NO3 minus, H2PO4 minus, PF6 minus, cesium ion, and then this very important quaternary ammonium ion. You can see that all of these ions have mostly different charge, size, and possibly they have different geometry. So all of these factors will actually affect the adsorption of these ions on the surface of this electrode. Now we have another class 1B, that is the ions which adsorb to a much greater extent than class 1A ions, because the attraction between adsorbate and electrode extend beyond simple Coulombic force to covalent bonding with the electrode by the donation of adsorbate electron to the orbitals on the electrode surface, and therefore bonding is happening. So anyway, both of these ones, that is the class 1A and class 1B, is constituting the class 1 compounds. So class 1B consists of these chloride, bromide, iodide, and then we have sulfate and thiosulfate, and then this cyanate ion, and then this another anion present over here, and all of these are really important, and you can see that they have different solvation as compared to class 1 compound, but they can actually go and bond to the surface of the electrode and can kind of chemisorb on the surface of electrode, and therefore this will be an entirely different situation. So then we have class 2 adsorbent material, and class 2 adsorbent material consists of neutral organic molecules. So neutral organic molecules are there, and they adsorb on the electrode surface due to the hydrophobicity in aqueous solution. So It means that if you have more hydrophobicity, then it will lead to more adsorption, more hydrophobicity and more adsorption. Bonding between the electrode surface and pi electrons and nitrogen lone pair electron of the molecule can enhance adsorption. And again, it is related to hydrophobicity. Their typical examples are camphor and butanol and quinoline. So these are class 2 materials and they are very common. So adsorption mechanism of class 1 and class 2 material can be seen over here. We can see that this is the adsorption of the neutral organics, and you can clearly see that if the surface charge is, this is a surface charge over here, if it is 0, then neutral organic molecules are showing maximum adsorption, and then the anions are showing more adsorption from 1b as compared to the anions which are coming from 1a class. So obviously it means that the hydrophobicity is playing its role, since hydrophobicity is not actually just related to the pi electrons and its interactions. Therefore these anions are adsorbing more on the surface of the electrode. So here is a dependence. So adsorption of anions and cation is enhanced by the electrostatic attraction with an oppositely charged electrode. The greater adsorption of 1b anions compared to 1a anions is evident. Now we can extend this further, that neutral organic molecule adsorb to greatest extent on an uncharged surface over here, as I mentioned earlier, and the electrode become charged, positively or negatively charged, then the adsorption will differ. That is, the neutral molecule are displaced by oriented water molecule whose dipole charges become attracted to the electrode, or by specifically adsorbed anion. So we are talking about, we are talking about this one. Okay, so let's try to draw it. So let's say that this is the electrode and here is the surface to this side. So let's say these are the solvent molecules, then this is A and this is solvent molecule. So you can see that this anion is specifically adsorbed. So we are talking about this specifically adsorbed anion, and this will actually affect the whole situation which is discussed over here for a positively charged electrode. So I will just remove this. Okay. So some organic molecules have been shown to orient in a specific geometry on the electrode surface, and some exhibit more than one orientation depending on the electrode potential and solution concentration. So again you can see that geometry become important under certain conditions. For example, if you are working on capacitor material, then geometry will be really important, and it will actually it will somehow affect or restrict the adsorption of certain ions and allow the adsorption of other, and this way a certain type of electrical double layer can be formed which will affect the performance of the capacitor material. Now we have class 3, class 4 and class 5 material. Class 3 materials are cations such as these metal ions over here, zinc, cadmium, tellurium and lead, which do not adsorb when in solution with non-adsorbing anion, but they can actually exhibit induced adsorption. So they can actually exhibit induced adsorption by strongly adsorbing class 1b anions such as iodide. Such induced adsorption involve the formation of surface complexes and sometimes crystalline bilayer with the adsorbed anion. Class 4 adsorbate are transition metal cation, those adsorptions are induced by complexation with NCS minus and N3 minus anions, both of which adsorb strongly on the mercury. That is, we are talking about the hanging mercury electrode over here. So on those kind of system we see the class 4 adsorbates are adsorbed. Then we have class 5 adsorbate, which exhibit metal-metal bonding between an adsorbed complex such as ruthenium complex and a mercury electrode. Now there are some other mechanisms like electron coating and modifications mechanisms, in which, for example, rapid polymerization of some species generates organic radicals which cover electrodes with a film. These films are quite tough, impenetrable, and cannot be removed. And due to these reasons, they actually passivate the electrode surface. And a typical case of this type of process is the 1,2-diaminobenzene. And the oxidation of an electrode, such as mercury in the presence of an anion, such as bromide, forms a film of insoluble Hg2Br2 on the electrode surface. And this formation of films with sulfur containing compound have its own effects. That is, it causes difficulty in use of mercury electrodes in biological media because the surface of the electrode is passivated due to the presence of this film, which is insoluble and formed over the electrode surface. Now here we see the effect of adsorption on the electrode response. So you can see that, and this one is basically showing the electrocapillary curve of camphor in acetate buffer. And if you look at the upper curve, that is the A curve, that is without camphor, and the second one is when camphor is added into the system. So what we see is that there is some pronounced inhibition effect on the curve during the process. Now the second one over here is polarogram of the process, which is actually happening in 0.009 molar EDTA and 0.001 molar copper 2 ions in 0.1 molar acetate buffer. So again, when camphor is added, you can see a pronounced dip in the response of the electrode. So we can say that the adsorption actually inhibits the response of the electrode of a process. Similarly, the adsorption can cause its own wave in a process, as you see in this figure, that due to the adsorption, we see a wave over here, which is showing that it is actually not part of the response, and somehow it is damping the actual response which is coming over here. So if there was no adsorption, it will be a smooth curve. So adsorption causes actually adsorption waves in certain processes. Similarly, it can do other things, like it can affect the potential of the outer Helmholtz plane, which was studied earlier. The presence of adsorbed ion can alter the potential of the outer Helmholtz plane, and therefore it can influence the rate of charge transfer. And then it can also do like some other things. For example, a specifically adsorbed anion causes the potential at outer Helmholtz plane to become more negative, and otherwise it would have been not that negative in the absence of the adsorbed species. So now it is end of lecture. So hopefully we will meet soon in another video, and you are advised to just look into your course and study the relevant material in detail so that it is helpful.